Any questions about any of the information we've covered? Any of the quizzes, any of the homeworks, any of the lab expectations, which we did make sure we covered last week? Anything there? You guys just want to go ahead and we'll just get after it and lecture? Yeah, so lab 6, the idea is you would in theory have a partner to do the skin fold calipers, but you're only going to have one partner that you're going to be doing that with. We got the skin folds sitting inside the lab when you first walked in. You guys want, feel free to check them out, make sure you're cleaning them, make sure we're wearing gloves, grab yourself a pair. You're going to be wearing your, obviously your mask, and we also have face shields available in the lab as well, which you guys can obviously take one of those and have that for your own personal use. So make sure you guys go ahead and grab those. And then, yes, the lab's open so you guys can do the vertical jump on the jump mat in there, along with for your lab 5, remember you're going to go and do that at the gym on your own, but we're going to make sure we're going to bring and go and tabulate our data and talk our way through it whenever we meet on Friday. So, all right, without further ado, we're moving pretty solidly through the class. I'm pretty happy with the rate we're going. But we're going to go ahead and now get into the pulmonary part of exercise physiology. So we're really looking at effectively breathing. We're looking at then obviously the volumes we're doing of that, how much that air we're getting to actually diffuse across the barriers there, how we're going to move oxygen and carbon dioxide around our body, and then the exchange we're going to have inside of our muscles, as well as how we're going to regulate our breathing rates. So now, as you'd suspect, your breathing system is there to effectively carry oxygen to the tissues that need it and remove CO2 and other wastes. But we're referring to obviously just gases in this capacity. Now, this is going to be obviously occurring through our the breathing part. So that's the ventilation. Then diffusion, which is going to be that air going from the inside of the alveoli of our lungs to inside of our blood. Then we're going to transport those gases via blood, aka mostly bound to hemoglobin, specifically with oxygen, and then with carbon dioxide as Carbaminohemoglobin, bicarbon, and then free-form carbon dioxide. And then how we're going to diffuse that into those cells, and that is internal respiration. So what we have here on the right is just kind of a basic image of an individual breathing into what's known as a spirometer. That's what we have in the lab, and you'll be doing that lab later on your own, where you're going to exhale. When you exhale, it's going to fill the spirometer, which is going to move, and it's going to show the total volume of air that happens to be going on. Now, your normal breath is referred to as your tidal volume, or that's just how much you're breathing at the time. Now, from there, we have what's known as our vital capacity. This is the biggest breath in you can take, followed by the biggest breath out. You can go ahead and push everything out. So the total amount of air that you have that you're capable of moving. Then we have what's known as the residual volume. And this is going to be effectively how much air is still going to be in your trachea, in your bronchi, inside of your nose, your mouth, because you can't collapse those. There's always going to be some air left over. Along with, we're going to have that, if we add those together, we have our total lung capacity. So the sheer amount of air that's going through this entire system. Now the actual ventilation, remember, we're going to be changing up air pressure so that we in turn going to be pulling air into our lungs by creating a vacuum when we're inhaling, and we're going to be pushing air out by creating more pressure inside of our lungs when we're exhaling to drive it outside of our body. Now, once we go through the mouth, through the nose, down through the phalanx, the larynx, and then the trachea, we get into the bronchi and then the bronchioles, and then finally into these individual alveoli, which is these little grape-like clusters where we're going to have the actual capillaries for our gas exchange. Now, the lungs itself are wrapped in pleura. They happen to have a viscera between the inside of your rib cage and the inside of your lung. For effectively, there should be a lower pressure there that keeps them together. If it's ever higher, you have a collapsed lung. That's a bad thing. So your lungs are going to take on the size and shape of your rib cage. So bigger rib cage, bigger lungs, smaller rib cage, smaller lungs. And like anything else, this is in turn effectively influencing how we're going to have these systems work. What's fascinating is when you exhale, the first air to leave is the air that was actually in your nose or your mouth. Followed by that was in your pharynx, followed by that was in your larynx, followed by what was your trachea. So you're really inefficient. Of your first part of your breath out was plain air that you got nothing from. And then arguably some of the first part of the breath that you're breathing back in is the air that you already had inside of you that happens to have had oxygen extracted and still higher amounts of carbon dioxide. The joys of an inefficient breathing apparatus, but it's the best we got. Some birds have a one-way breathing system, which makes them far better aerobic athletes than us. Now, notice when we're inspiring the air, so we're breathing in, we're going to do this by effectively creating a vacuum. That's going to go ahead. The diaphragm is going to flatten, so it's going to pull the lungs down. The external intercostals are going to move up, so we're going to spread the rib cage. And from there, we're going to go ahead and create that vacuum that's going to go ahead and pull air into the lungs. Notice, guys, the intrapleural pressure, so that's between the lung, the diaphragm, and the essentially the cavity of the rib cage. We want that to be lower because it's keeping the two adhering. If it's ever higher, once again, collapse lung. So from there, our lung volume is going to increase and the pressure inside of it is going to be lower. So this is naturally going to create that vacuum that's going to pull air in through the nose and the mouth into the lungs itself. And so this is just due to the simple pressure differences. Now, when we start really breathing at a much higher rate, we're going to use our scalenes, our sternocleidomastoid, even our pectorals, so we can really lift those ribs up. So we're going to be able to take a deeper breath and obviously get more oxygen to go through our body. Now, expiration, we have the opposite. The diaphragm is going to push its way up. The rib cage is going to come down, which in turn is going to create this greater amount of pressure inside of your lungs, which in turn is going to be pushing air out of your body. Now, this can also be an active process. Typically, just breathing in is going to be mostly from your diaphragm, and exhaling is going to be a relatively passive process. But if you want to push, we're going to use our internal intercostals. Okay, we can use our lats, our QL, and our abdominal muscles to really force the diaphragm up so that we're going to be able to get more air out of our lungs. So think if you were trying to blow up a balloon or otherwise, you would have to use that greater amount of force. Now, what's interesting is what's going on inside of the body is thanks to these pressure gradients, remember we talked about a little bit last week with cardiovascular physiology, in turn, this pressure is going to cause compression on side of our veins. And then when we have that negative pressure, it's going to give us a greater amount of venous filling. So that allows for a greater amount of blood returning to the heart as we go through our normal breath cycle. And also that same type of pressure is going to influence vagal tone. So when you're breathing out, you're actually increasing your vagal tone. So your heart rate in theory can go down a little bit. When you're breathing in, you're increasing your vagal tone, so your heart rate's going to go up a little bit. And the difference between the two is what's known as heart rate variability, which can be an important indices of looking at individual recovery. So when it comes to the general blood flow, when we're looking at the lungs at rest, we're going to get all the blood that's going through the body is the same amount that's going through the lungs. It's as we increase our exercise intensity, because we've got a greater amount of blood output through our left ventricle, it's always going to match with our right ventricle. Now notice the pressures here are massively different. The reason for it is you don't need that high of pressure to go through your lungs because it's not as great of a distance. And it doesn't happen to have as much pressure to work against to have that gradient. So it's going to be able to cover that distance, unlike the left ventricle that has to overcome the aorta. So what we're going to find is that initial air that we're breathing in is mostly nitrogen. Only just shy, so it's 20.93% of that is oxygen, and about 0.03, getting closer to 0.04 percentage of the air you're breathing is actually carbon dioxide, but most of the air you breathe is nitrogen. So this is, if we take each of these individually, we're going to effectively see what is known as Dalton's law below. So we have our total air pressure. So it's usually around 760 millimeters of mercury. That is going to change, obviously, depending on if we're low pressure, which is usually when there's storms, or high pressure when it's relatively clear. All of those individual pressures, so the partial pressure of nitrogen, so you take that percentage nitrogen, multiply by 760, you get 600.7. Same thing when we go with oxygen, carbon dioxide. If we add all of those three together, they're going to add up to the total air pressure, okay? This is what's known as Dalton's law. Airs or gases are going to effectively get, thanks to the percentage they make up of total air, you multiply that by its air pressure, and that's its partial pressure. And this is going to become important in a few moments, because then when you tie that into what's known as Henry's law, which is where gases are going to dissolve in liquids in proportion to their partial pressure, this explains the issues of being up at altitude when it comes to your ability to exchange oxygen. So this is obviously going to always depend on the medium that it happens to be passing through, the temperature it happens to be, solubility, etc. So if we see that partial pressure, okay, that's the most important factor for determining the gas exchange. So the higher this partial pressure, the easier it is to diffuse the gas across the gradient. The lower the partial pressure, you're not going to be able to get as much gas to go across, or none at all. So why we care about this is because the actual air inside of your lungs is incredibly humid, okay? See how the partial pressure of dry air is 0, but when you go to alveolar air, we got 47. This is why you can see your breath when it's cold. It's completely normal because of the amount of water that happens to be inside of it. Now, this naturally, because we've increased the amount of H2O, we're going to have decreased the amount of oxygen available. Mind you, you're going to see a little bit lower availability of nitrogen. Carbon dioxide is simply higher because that's where you're doing all this gas exchange. Now, this is important because notice we're going to completely top off our arterial blood pressure when we're at sea level. Now, as we go up in higher and higher altitudes, the air pressure becomes lower and lower. And as that air pressure goes down lower, in turn, we're going to have much lower saturation of our actual red blood cells. And since our oxygen saturation is going down, our body's going to work harder at rest, increase that cardiac output. So we're still getting the same amount of oxygen to our tissues on average. And this is kind of what can lend itself to the beginnings of altitude sickness. So what we're going to find, again, guys, is we start off with that atmospheric pressure, partial pressure of oxygen being at 159. Now, once we get to alveolar air, because of the effects of H2O along with a higher amount of carbon dioxide, we're going to get about 105. Now, when it's returning through the pulmonary artery, so this has been mixed blood that has on average about 40 millimeters mercury, can be lower, especially when it gets to the capillaries coming right off of exercising muscle. We, in turn, are going to go ahead and see that total amount of oxygen available is relatively low. Now, this gives us our total gradient of 65 millimeters mercury of effectively, we're going to get up to about 100 millimeters mercury in the pulmonary veins, meaning right before we get back to the left atria, which in turn left ventricle, and then on to the rest of the body. Now, with carbon dioxide, if you guys can see in here, we have the PCO2 of 40, which is going to be about topped off. We're only getting up to about 46, but that's coming down to some interesting effects of how we're getting gases effectively to diffuse, and carbon dioxide is one that's much more readily diffused. Now, Fick's law is going to be the rate of diffusion is proportion to the surface area and the partial pressure gradient. Now, why we care about this? Because it turns out those gradients are important so we can saturate. They have to be larger for oxygen because it turns out its diffusion is not that great. And what we're going to also see is it's not just going to, it's going to be the thickness of the membrane it's diffusing across along with the surface area that's available. So if we increase the surface area and we decrease the thickness, in turn, we're going to do a much better job of gas exchange. That's why your alveoli are very thin. And because of all of those grape-like clusters you have all over your lungs, it massively increases the total potential surface area that you're going to have inside of your lungs that they're going to be able to occupy. So our total amount of oxygen that we happen to be diffusing, and this is going to be simply per minute per millimeter of mercury gradient. So when we're really looking at capillaries, we're looking at about 11 millimeters mercury. Now, our total resting, okay, is going to be about 21, notice, mils per minute per millimeter of mercury. Or this is going to be effectively 231 mils of oxygen per minute, or just that 11 millimeter mercury gradient you're going to see between. Okay. Now, when we start exercising, we're going to do a better job of extracting oxygen. So the venous oxygen is going to be lower, which gives us a bigger gradient. And this is going to allow for more oxygen to diffuse. Now, the other thing that's important is at rest, we're not actually getting that great of oxygen diffusion because we do not have really good blood flow to the entirety of your lungs. So thanks to the effects of gravity, the bottom third of your lung is going to be really, really perfused with blood. The middle third is definitely not that well diffused, but your upper third is very poorly diffused because your right ventricle isn't working that hard. It's not pushing the blood through that aggressively because it doesn't need to. Now, as we increase exercise intensity, we're going to improve this oxygen diffusion through all of the different portions of the lung. And because of this, we're going to have a much better oxygen uptake because we're getting much better blood flow to these areas. Now, oxygen itself is going to be transported in the blood for the majority bound to hemoglobin. And remember, hemoglobin is going to be that iron, well, it's got the iron fixing in the side, in the heme unit of the 4-globin protein that makes up hemoglobin. And that is going to be made up of millions of these individuals inside of an individual red blood cell. So millions of hemoglobin in one red blood cell, which is going to allow for the oxygen carrying capacity. Now, 2% or less is going to be actually dissolved in your plasma. And this is what they're kind of looking at when they're measuring your saturations, kind of looking at, well, how much is there, and that's kind of an inference along with obviously how much is in your hemoglobin. Now, hemoglobin is interesting because it's not a straight up 1-to-1. The higher the pressure of oxygen, the higher its saturation. Instead, it's going to work itself across a bit of a curvilinear relationship. And that we're going to find is that once we get up to those highest levels, the affinity, so how much of hemoglobin is going to be 100% saturated, is going to be pretty high. It plateaus once we're really getting about above 80. But once we start to drop down a little bit, it drops down drastically once we get to the low end of the curve. Now, this is a good thing because this means exercising muscle that's really extracting every last oxygen it can from hemoglobin. It's going to shift this curve and be operating over in this area. So it's going to do a much better job of taking that hemoglobin or taking that oxygen from hemoglobin. So that way it can be picked up by actually myoglobin inside of the muscle and then transported into the mitochondria and utilized for energy. So effectively, it allows us to load up and top off quickly, appropriately in the area, but then hold that for where we need to until we get to the point at which we have a low partial pressure of oxygen, which once again is around that exercising or very metabolically active tissue, and it's going to unload it rapidly. The reason we say it's 40 at rest is because the blood, when you're just at rest, yes, it's pumping everywhere in your body. But yes, you're sending it to your brain, your kidneys, your digestive system, and that's really the one that's firing the most when you happen to be at rest. Now, as we start to exercise, we're going to ship more blood over to our muscles, but also we're going to be extracting a lot more oxygen because muscle, once it really gets going, is a lot more metabolically active than any of your other tissues. At rest, very, very different story, but in maximal exercise, quite higher. So what we're going to also find is that relationship, the curves of saturation are going to be influenced by both pH and temperature. So when the pH is lower, it's going to more rapidly offload oxygen. When the temperature is higher, it is going to much more rapidly offload oxygen. Why do you guys think this would be so? What do you think the advantage is to offloading oxygen faster when the pH is lower, so more acidic compared to higher, more basic, and to offload oxygen faster whenever the temperature is higher as opposed to being lower? Yes, what is the advantage? Why would we want to offload oxygen faster when the pH is lower? Anaerobic glycolysis, exactly, guys. So if we have an exercising muscle that is using anaerobic metabolism, we're going to do a really good job of offloading oxygen to that area. That's what we want. So we're going to actually do a better job of performing. So the maximum amount of oxygen we're going to carry is going to come down to how much hemoglobin we actually have. So if we have got 12 to 18, so you can have low and high hemoglobin. Lower, obviously not as great. High, carry way more. And it obviously can get to be too high where we can have an issue. Well, that's going to give us our saturation where we have at rest. And we're only using about 3/4 of a second to get that to transit around our body. So we're not going to have as much saturation actually when we're exercising because we're pumping that blood so quickly through our lungs. It's not going to be able to get up to the higher level of saturation, but at the same time, it's still going to be really good. So 1 gram of hemoglobin is going to bind 1.34 milliliters of oxygen. So normal blood, so it has a normal healthy amount of hemoglobin, we're talking about 16 to 24 mils per 100 mils of blood. Now, obviously people that are anemic, so they've got less red blood cells, in turn are going to have a lower amount of hemoglobin and in turn a lower oxygen carrying capacity. And guess what type of athletes that's going to really negatively affect? Absolutely, guys. Endurance athletes. Good job. Now, on the other side, we have carbon dioxide. And remember, this is a natural waste product of breaking down fats, carbs, and obviously amino acids aerobically. And so it's going to be carried away in 3 different ways. One is by carbonate ions. That's actually going to be the major component of it. Some dissolved in plasma, and then some actually bound to a different location than the heme group on hemoglobin. And that's going to create what's known as carbaminohemoglobin. So 60 to 70% of that is going to be in the form of bicarbonate. So when we literally put carbon dioxide and water together, we're going to form carbonic acid. So that's just H2CO3. This is absolutely normal. It's going to occur in the red blood cells, and it's going to be catalyzed by the enzyme carbonic anhydrase. Now, this in turn is going to dissociate into what's known as bicarbonate. So we have HCO3 and then a free proton. So this in turn is going to, the proton bind to hemoglobin because it buffers it out. It's going to trigger what's known as the Bohr effect. And in general, what we're going to find is this bicarbonate is going to leave the red blood cell and go into the plasma. Now, bicarbonate is not a bad thing. It actually is going to do a good job of keeping us from having our pH go too low. And hemoglobin is actually a bit more efficient when it happens to be around notice that acidic environment. Now, only about 7 to 10% of that is actually, of the CO2 is actually just plain old dissolved in your plasma. Now, this in turn, when your amount of partial pressure of carbon dioxide is low in the lungs, that CO2 is going to come out of solution and then going to diffuse out into the alveoli. Now, that carbaminohemoglobin, where it's going to bind to a different location than where oxygen binds to, is going to be about 1/5 to 1/3 of the way that carbon dioxide is going to be transported out of the body. Now, this is going to not bind to the heme part, it binds to the globin portion. So it's just the other part of the protein. And in turn, this is going to be influenced by effectively the amount of oxygen available. So in really carbon dioxide. So it's going to bind a lot easier to hemoglobin that doesn't have oxygen on it. And when we have higher and higher amounts of carbon dioxide, we're going to be doing a much greater job of causing this binding to occur. When it's lower, dissociate, which makes sense. So when it's higher, we're going to pick it up and bind it. When it's lower, we're going to drop it off. And that means we're going to pick it up at the muscle, drop it off at the lungs. So the capillaries of each, always remember that's where we're getting the gas exchange. Now, we need to understand effectively how much gas we're taking up. And this is going to come down to what's known as the AVO2 difference. So what we really have is the amount of oxygen we have in the arteries compared to the amount of oxygen that shows up in the veins. So however much this decreases by gives us our AVO2 difference. So that's literally how much oxygen was extracted. So The higher this difference, the better job we're doing of extracting this amount. So, for example, when we're just looking at a muscle at rest, notice it's going to extract a little bit just because it needs to maintain itself, constantly has a lot of functions going on to make sure everything's operating appropriately. Now, when we get into exercise, this is where we're going to start to really, really extract the vast majority of oxygen that happen to have gone through those capillaries around those individual muscle fibers. And the other thing to keep in mind, guys, it's not just hemoglobin in our blood, it's also myoglobin inside of our muscles. Now, myoglobin is going to be the oxygen carrying protein that literally exists inside of our muscles. Now, notice it has a much higher affinity for oxygen, isn't going to drop it off until it's have really, really low amounts, which is good because it's going to effectively take oxygen from hemoglobin and drop it off into the mitochondria, because it turns out the mitochondria is going to use the oxygen it has available really quickly as the final electron acceptor of the electron transport chain, and it's going to keep its partial pressure of oxygen is going to be insanely low. We're talking always going to be way less than 20 millimeters mercury. So it's going to effectively rob hemoglobin, drop it off in the mitochondria, and repeat. So it's going to be loading effectively at 20 millimeters and above. But then once we get down to 1 or 2, that's where it's going to be dropping it off. And once again, your oxygen amount that you're naturally going to store inside of your mitochondria is about 0. So it's going to rapidly drop it off in those areas. Now, obviously, how much oxygen we're taking up and how much we're dropping off is going to be influenced by a number of different factors. First and foremost, how much oxygen do we actually have in the blood in the first place? If we have less in the first place, we're not going to be able to take up as much into those tissues. If we don't have as much blood flow to those tissues, we obviously are not going to be able to deliver as much oxygen. And then obviously, when we talked about earlier, the effects of pH and temperature. So when do you guys think we'd run into a situation where the oxygen content of the blood would naturally be lower? Because blood flow makes sense, because at rest, you don't have much blood flow. Absolutely. And then as you exercise, it's going to go more and more sort of the muscles. And we've already beat that horse with, it turns out, the lower the pH, the higher the temperature, the more we're going to be unloading in those areas. But when situationally do you think we might have an issue with not having as much oxygen in the blood in the first place? So right off of the capillaries in the lungs, we're not saturating out as well. What do you think could cause that? Probably not so much with deformity of the vessels. I mean, if you did have some issues with capillarization to tissues, that is a possible situation. I guess I should have probably said that I'm trying to not talk about disease states, but way to think outside the box. Not necessarily not feel well, but you could be, great point there, Noah. Yeah, you could be effectively breathing unrecycled air, so the partial pressure of oxygen is naturally dropping, and because of that, you're not going to have as much top off. Feeling well is probably not going to be an issue so much unless you're anemic, because that's going to lower your oxygen carrying capacity. And the other one, guys, which is only going to really happen to you guys if you travel to certain locations, which is going to be being at elevation. Because we're up higher in elevation, the partial pressure of oxygen goes lower, and in turn, our oxygen saturation is going to be naturally lower. And because of that, we're going to, in turn, obviously not be getting as much oxygen going to our areas of our body. Now, carbon dioxide is going to be leaving our cells through basic diffusion, and that's going to obviously go, thanks to the gradient of it's much higher in the muscle, than it is going to be into the blood. And then remember, once there, it's going to be mostly into bicarbonate, followed by carbaminohemoglobin, and then finally as just plain old carbon dioxide. Now, we're going to be regulating our ventilation through our body's ability to sense the amount of carbon dioxide and the amount of pH that happens to be available, or sorry, carbon dioxide, oxygen, and what happens to our blood pH. So you can actually trick yourself into not feeling like you need to breathe as much by hyperventilating for a little while and then holding your breath and slowly off, because you're going to naturally lower your partial pressure of carbon dioxide. So you can actually give yourself a longer period of breath holding if you're wanting to, because you're effectively tricking your body into thinking you don't have as much carbon dioxide. And in fact, tolerance of higher amounts of carbon dioxide in the bloodstream is usually a pretty good indicator of effectively people's best baseline anxiety and otherwise. Now, you guys all know what that drive to breathe feels like. So if you try to hold your breath for a really long period of time, you're going to keep having more and more effectively carbon dioxide accumulate, along with if you're exercising, you have that drop in pH. And in turn, that's going to go ahead and tell us that we need to go ahead and breathe. Now, notice when we feel that stretch on the lungs, it's going to tell us to expire. If any of you guys have ever been going really fast on with wind blowing in your face, could have been like on a bike, in a convertible, or otherwise, you can sometimes feel it feels a little awkward to breathe in when you have air blasting into your face, because your lungs don't want to overstretch, because if you overstretch and you pop a lung, you're going to die. So the body wants to, or you're not going to die, but you're going to really increase the risk for that. Your body wants to mitigate any potential risk of doing those things. And so we're going to have our muscles contract, which in turn is going to get us to go ahead and breathe out. Now, we do have obviously conscious control of our breathing, but this is going to be something that is going to be mostly regulated through more involuntary mechanisms, which we can obviously override if we need to. So we have our inspiratory and expiratory centers, which happens to be in that brainstem. So we're talking lower. We're talking about medulla oblongata, and we're talking about our pons. This is where we have our rate, our depth of breathing, where we're going to be telling ourselves how much we need to. Now, our cortex can always override this if it needs to. And this is mostly going to be by sensing the amount of carbon dioxide in the cerebrospinal fluid. So when that amount goes up, it's going to tell us to increase our breathing rate and our depth and remove that carbon dioxide. And you guys know that feeling of discomfort you can have when you're trying to hold your breath, or you're trying to purposely slow down your breathing when you're exercising, because your body's like, no, you need this oxygen or you're going to die, which is a good reason for your body to tell you you need to breathe, because it turns out that would be a bad way to take yourself out. So we then have peripheral chemoreceptors, and this is going to be in the aortic bodies and the carotid bodies, where we're going to be sensing the amount of oxygen, carbon dioxide, and those wonderful protons that happen to be in the bloodstream. So if we happen to have greater amounts of protons, we in turn are going to go ahead and increase our breathing rate, because it's actually a way that we can increase our pH is by hyperventilating. Now, we also touched briefly on those wonderful mechanoreceptors that's going to feel effectively the stretch. So if we feel like we're under stretch, so like the air is blowing in towards us, this is going to naturally reduce our depth of breathing. And this is going to lend itself to what's known as the Herring-Brewer reflex that's going to naturally modulate this, so we don't risk, once again, injuring ourselves. What questions, comments, concerns do you guys have about anything we talked through on chapter 6?